In this video, we're going to go over some examples of projection of vectors onto each other. Before I go into the examples, I want to kind of draw a picture to offer some intuition behind what we're going to do. Suppose that we start with two vectors, a vector u and a vector v. And if we want to project a vector u onto a vector v, what we can do is we can kind of think about it in terms of if there was like a light above u, and this is, we're looking for the shadow of u on v. And in finding this projection, there are two different pieces that we can find. We can get the scalar projection, which gives us just the length of this vector along here. So that's u dotted with the vector v divided by its length, okay? So this guy right here, this is just a number, and it gives the length of the projection. The other part of the projection that we can find is actually the vector itself. And this is given by, well, the length, which is just the scalar projection. But we also need to actually make it into a vector, which means we have to give it a direction. So we have its length, now we just have to give it direction. And notice that the projection lies along v, which means that we want it to have the same direction as v, but we already have its length, so we need v to not contribute any length to it. And the way that we're going to do that is just multiply it by v divided by its length yet again. And intuitively, maybe the way that we can think about this right here is that it gives the part of the vector u that points the same direction as the vector v. And this number right here is a measure of how much they have in common. And this piece right here simply gives direction. Okay. And if we want to look at an example of this, just to make it a little bit more concrete, let's take our vector u to be equal to 3, 4, and v to be equal to 0, 3. And let's put them on a coordinate plane. All right, so our vector u is at 3, 4, so it's going to be out here like so. And our vector v is 0, 3, so it lies along the y-axis like so. Now, if we want to take the projection of u onto v, it's just going to be the part of u that lays along v. So think about it as casting a shadow down this direction. So it's going to look just like so. But how do we actually find the values that are associated with this? So to get the scalar value, we're just going to take u dotted with v divided by its length. That's equal to the vector 3, 4 dotted with, and then the length of v is 1/3, and then v itself is 0, 3. So we get 0 plus 4 times 1, and that is just equal to 4. So 4 is the length of this vector right here, that projection. To get the vector part, we take the length given by u dotted with v divided by its length. And then we multiply that by v divided by its length again. And in this case, we've already found its length right here, which is 4. And now we just have to multiply that by 1/3 times the vector v, like so. So we're going to get 0, 4 as being the vector or the projection of u down onto v. And this kind of makes sense. We can see that here where 0, 4 being the projection. So this vector right here, we drew it just to see what it looked like. This is indeed actually the vector 0, 4. This projection process has a really important property of it in that it allows us to be able to split vectors into 2 distinct pieces. They're called a parallel. There's like a parallel and then an orthogonal part. So we're going to talk about an example with that as well. Okay, so why can we do that? Let's go back to our picture of u and v and its projection. So here's u. And here is our vector v. And suppose now that we want to project u down onto v. Well, notice that we're taking u and we're imagining that it kind of collapses down vertically onto v. So it winds up with this vertical component here. And then it has the horizontal component here that is actually the projection. I'm going to call this u, and then that's just the little parallel bars there. And notice that since this is vertical and this is horizontal with respect to v, this angle right here is a right angle. So we then consider this to be our orthogonal part. And notice that since this vector goes from the end of this one, or the beginning of this one to the end of this, this vertical part right here, we can consider u to be equal to that projection plus the orthogonal part. Remember that this guy right here was given by u dotted with v divided by the length of v times v divided by the length of v. And then this guy right here, you can almost think about it as kind of being like the leftover part from having this piece subtracted out. So we can take u perp and write it as equal to u minus, and then that projection part. And this way of breaking down a vector into an orthogonal or a perpendicular part and then a parallel part is actually, it's going to play a really important role moving forward. And then also if you ever take any higher level math classes like a matrix theory or a linear algebra class, you're going to see this pop up all the time. So let's work an example of this. So in this example, we are going to break down a vector into its 2 pieces, the parallel and the perpendicular piece with respect to another vector. So we're going to find the decomposition of a vector A. We want it to be equal to its parallel part plus its perpendicular part. And we're going to do this with respect to the vector B, where we have A equal to the vector 2, 7, and B equal to 3, 5. Okay, so before we launch into doing this problem, I always like to draw pictures, so that way it kind of helps me keep track of what I'm trying to find and what I've already got and all of that stuff. So let's draw A and B and look at the different pieces that we're trying to pull together. All right, so our vector A might look like that. Vector B maybe looks like so. And when we're looking for that parallel part, what we're really looking for is just the projection of A down onto B. I should probably label this vector. So it's going to be this piece right here, that projection down onto B. And since it is just the projection, we do actually have, that formula for it that we can use. So that's going to be the A dotted with B divided by its length, and then multiplied by B divided by its length again, just like so. And then the other piece of this decomposition is that perpendicular leg that gets left over, or the vertical part, like so. And we're going to be able to compute that by simply just taking the difference between A and then that parallel part, because it's really just thinking about what does A look like if this piece wasn't present. But because this part, we don't really know this part, and we don't know this part yet, so we can't really compute this piece without this. So we're going to start with the parallel piece first, because we actually have a formula for that using entirely information we already know. So that's A dotted with B divided by its length times B divided by its length. And that is equal to, just kind of rearranging this a little bit because it makes the math simpler later on. We're going to take A dotted with B divided by its length squared. And then it winds up just being times B on the outside there, like so. Okay, so let's start plugging some values in. We're going to get A replaced with 2, 7. Dotted with, and then the length of B is root 34, so when we square it, we're just going to get 1 over 34, and then times B itself is going to be 3, 5, and then this is all multiplied by B once again. So for that dot product, what we're going to wind up with is 2 times 1 over 34 times 3, plus 7 times 1 over 34 times 5 times the vector 3, 5. I'm just going to leave all of this added together, and on the outside of that vector, you're going to get 3, 5 scaled by 41 over 34, like so. So that's our parallel, or that projected piece right there. Now we've got to find our second piece of this decomposition, which is the perpendicular or orthogonal part, and that's given by A minus its parallel part. So plugging the values in that we have, it's 2, 7 minus 41 over 34 times 3, 5. Doing all that computation, simplifying it down, you're going to get negative 55 over 34. And then 33 over 34 for the second component there. So if we kind of want to put it all together and see what it looks like, the decomposition would be given by 41 over 34 times 3, 5, and then plus that orthogonal part, negative 55 over 34, 33 over 34. So that's your parallel part, and this is your orthogonal part.